Thanks for coming. For me, this is spring weather coming from Chicago. Although I don't like the freezing rain either, so I'm not going to trying to figure out what to talk about, and I'm not going to talk about partial identification or about identification at all. In fact, instead I'm going to talk about a straight statistical issue, and I know this is a OPR, so you do population studies and surveys, and I don't know how many people in this room do randomized trials, but even if you don't do randomized trials, everyone is aware of the influence of randomized trials on the social sciences and in medicine, and I think everyone is aware of the pernicious influence of hypothesis testing in randomized trials. So what I'm going to talk about is not really thinking outside. It is thinking outside the current box, but it's trying to get things back to a box which was prevalent in the 1950s, a long time ago. So that's where the title is. It's about treatment choice with trial data, and with a somewhat provocative subtitle: "The statistical decision theory should supplant hypothesis testing." I'm not trying to save hypothesis testing at all. I want it out and gone. And there's a context for this. You see, the paper will be out shortly in the next month in a special issue of the American Statistician, which is the kind of general audience journal of the American Statistical Association. And there's a provocative title for the special issue. This is the ASA, the Statistical Association, not Sociological Association. They titled the special issue "Statistical Inference in the 21st Century, A World Beyond P is Less Than 0.05. That's the actual official title. And it's a follow-on to, some of you may know this, in 2016, the American Statistical Association did something quite unusual for a professional organization, scientific organization. It actually made a public statement on the use and misuse of hypothesis tests and power calculations, significance, statistical significance, and all that. And then they decided to do this special issue as a kind of follow-on to that. So this is going to be out in another month. I'm told there's like 44 papers. It's going to be online only, open access special issue, and it's kind of a big deal. So I actually have two papers in there, and this is the title of one of them. And then if I get to it, I know you have a kind of a short seminar by economics standards where we go 90 minutes. And so I may not. We'll see how much I get to the application, which is to a medical clinical trial. So I hope I'll be able to say something about that. Okay, so to get going. What's in the box? The conventional use of hypothesis tests to compare treatments, which is thoroughly institutionalized in medical research, and it is very prevalent in social sciences as well. So if you think about having a very simple trial between two treatments, and often, particularly in the medical context, one is a status quo treatment, the other one's an innovation, then there's a usual null hypothesis that the innovation is no better than the status quo, and the alternative is that the innovation is better. And you do an absolutely standard hypothesis test. There should be a one-sided test under this, although sometimes they do two-sided for reasons that aren't clear. And if you don't reject the null hypothesis, then the treatment recommendation is the status quo should remain the treatment of choice. If you do reject the null hypothesis, then that's sort of evidence that the innovation is better than the status quo, then it's recommended the innovation become the treatment of choice. Now, the place where this is most institutionalized is, of course, in drug trials and the federal and the FDA actual institutional process for drug approval. It does exactly that you have to reject the null hypothesis actually on two independent trials to get a drug approved by the FDA. Now, I think as everybody knows, in the way that this is done, hypothesis testing is a very general idea, but there are very strong conventions about how you treat type 1 and type 2 errors, and that you do the test so that the probability of a type 1 error is 0.05. That's the magical 0.05, which has, absolutely no one has ever given any particular scientific background for this. It just became the convention. And so then so you care about the probability, so the type 1 error occurs if the null hypothesis is correct, but you reject it. And then you care about probability of a type 2 error. That's if the alternative is correct, but you reject that. And that's usually set not at 0.05, but typically at 0.20, or 0.10 to 0.20. So I have one quote from this is from a European document. You can find similar American ones that just, say what I think everybody knows, is that you use probability 0.05 for the probability type 1 error, and then 10% to 20%, it says here, for type 2 errors. Okay, so that's the way things are done. And this is not hypothesis testing for doing science, that there's some theory in the question of overturning the science. This is for treatment choice. This is for actual decision making, okay? And I want you to keep that in mind the whole time. Because if you want to argue that hypothesis testing is reasonable if you're a scientist and not making a decision, we can discuss that over a sufficient wine or beer. Because I don't know exactly what that means to do science without a decision problem, but a lot of people think they know that. I'm just going to stay away from that, okay? I want to focus on the use of hypothesis testing for making decisions. And the medical decisions are really a good example, because these matter in the world. Where a lot of social science randomized trials, it's not exactly clear what will happen as a result of the trial. In the medical trials, you have very specific things that are going to happen. Okay. So what's wrong with hypothesis testing? I have got a couple of slides here, both from a recent paper that I co-authored with Alex Tetenoff, who's at the University of Bristol. This is in the PNAS from 2016. I don't think, and what's on these slides is not really original. It's just our statement of things that have been said over and over again for more than a half century, particularly by Bayesian statisticians, who don't like anything that's frequentist, of course, but they particularly don't like hypothesis testing. And so these arguments have been made before, but I'll just state them the way that Alex and I make them, about 3 problems with the use of hypothesis testing. One is the one we just noticed, is the convention to use asymmetric error probabilities for type 1 and type 2 errors. Testing theory gives no rationale for these particular error probabilities. It doesn't explain, I talk about a clinician, because I'm always thinking a lot of my own recent work is actually on medical decision making. So I talk about a clinician making decisions. If a clinician cares about patient welfare, you care about choosing the wrong treatment. It's not worse to choose treatment A than B or B than A if they're wrong. It's both bad. You just want to choose the better treatment, period. So the idea that you should have a 0.05 probability of a type 1 error, but 0.20 is okay for type 2 error, hypothesis testing doesn't explain that. Okay, so I think everybody understands that. Second issue is equally important, but is given much less attention. But it should be taught on the very first day of a basic statistics course, is that hypothesis testing only pays attention to the probabilities of errors and not to the magnitude of the mistake that's made. Now, if you're thinking about, take the medical case, about how bad is it to make a decision of one type than the other, they may be very asymmetric. Okay, I like to use in my own work on medical decision making, think about, and this is a case I'll talk about later if I get to it, about choosing between surveillance of a patient and aggressive treatment. So surveillance, you just watch the patient and hope everything's okay, periodic scans and things like that, clinic appointments. Aggressive treatment, you go in and do something, okay? So, we know surveillance is actually a better thing to do if the patient's not really ill. Aggressive treatment is the better thing to do if the patient's really ill, but aggressive treatment may have side effects. So the mistakes from making, the magnitude of the errors, not just the probability of error, but what happens, if you do aggressive treatment and the patient's not really sick, then the patient suffers side effects. And the side effects may not be pleasant, but they may not kill the patient. On the other hand, if you do surveillance and the patient is sick, then the patient may die. So the magnitude of the losses may be very, very asymmetric. Classical hypothesis testing says nothing about that whatsoever. If you're thinking about from a decision perspective, you should weigh the magnitudes of the errors and not just the probability of the errors, okay? And that's really, it's just ignored typically. Third issue is more of a technical issue, but it's a big deal for those of you who care about the statistical analysis, is the classical hypothesis testing, you get a null alternative hypothesis and alternative. So that's fine for choosing between 2 treatments, treatment A and B. But what if you want to choose among multiple treatments? Many clinical trials, like multi-arm trials, you want to compare treatment A, B, C, D, E. How are you going to do hypothesis testing? So this is whole literature in statistics that's developed on so-called multiple testing problems, and it's kind of ad hoc and a kind of mess, okay? And that's because you really haven't been able to coherently generalize from the simple classical null versus alternative case to the multiple treatment case, okay? And that's more of a technical statistical issue. There are articles going back to the 1950s on it, so I'm just going to mention it. I'm not going to focus on it. So we have all those issues. Now, I've got a little example here. I'll just go through very quickly. You can read the slides. Just about how this matters is that imagine that you've got a status quo treatment and you know what's going to happen with that. This is like a terminal disease, and and patients maybe they're going to live for 1 year on average with the status quo treatment. And now someone comes up with an innovation, a new drug, and you don't know whether the new drug is going to work or not. So there are two possibilities. One is the new drug is great and it's going to increase lifespan, mean lifespan from 1 year to 5 years. Let's say for some really aggressive cancer, which would be great. But there's another possibility that it's really bad and it's going to decrease lifespan because it's toxicities and so on to 1/3 of a year, okay? So how are you going to do this? Well, traditional hypothesis testing would set the error probabilities at 0.05 and 0.20 and then use the result. But let's think about what happens here. If you commit a type 1 error with a classical test, you would permit yourself a 5% chance of an error, and then the loss that you would suffer would be 2/3 of a year because lifespan would be reduced from 1 year to 1/3 of a year. If you get a type 2 error, so that the new drug is really good, but you're going to let that happen with probability 0.2, and you're going to reduce patients' lifespan by 4 years, from 5 years to 1, if you don't take the new drug. So these things are very, very asymmetric. I don't think any clinician, if you just pose a simple example like that, would say this would be a sensible thing to do. So why you should be so much asymmetric about making an error of one type than another type. And classical testing just doesn't deal with that at all, okay? So you can keep that in mind just as it's just a made up example, but it makes the point. Okay, now the question is, what can you do? You say, well, what if we don't do hypothesis testing, what can we do? So this is where statistical decision theory comes in. So now I've been doing work on statistical decision theory since the early 2000s. My first published paper on it was in 2004. But of course it wasn't new. Statistical decision theory was developed in basically the 1940s and through the 1950s. And the classic reference is Abraham Wald's 1950 book. I do not advise you to read it. Wald is a straight mathematician, and there's like a few words of English in the book, and it's rough going. But there are of course textbooks and so on following it that are rigorous but are much easier to follow. I just want to give you the sense of what the Wald idea is and see how. And what we've been doing in the recent work is applying Wald's old ideas to this problem of treatment choice. So just let me spend a few minutes explaining what the ideas are. Wald said, well, why do we collect sample data? We collect sample data to help us make a decision. So what we want to do is pick what he called the statistical decision function, which is a function that maps the data into a decision. And what we want to do that is to do that in a reasonable way. Is to have a reasonable way of using the sample data to make a decision. So Wald is a frequentist. He's not a conditional Bayesian. He says, let's look at this ex ante across repeated samples. Because if we're going to draw a sample, we don't know what data we're going to get. And so we want to ask, on average, across repeated samples, how well will things work? So that's the same as in hypothesis testing. Is you ask ex ante how well the thing's going to work ex ante. And but instead of what goes on in hypothesis testing, he wanted to evaluate the quality of a way of using data by the distribution of, he taught loss. I'm going to talk about gains, welfare maximization. Wald just did it with loss. It's like, how bad is it going to be to use the data in a particular way across repeated samples? So that's what he did. And he focused on mean performance across repeated samples. The theory, basically, I can say it without any math at all. It's just when you dig into it, it gets very abstract. But the conceptually, it's very simple, is you have to first specify, I'll use decision theory language, specify a state space. It's what in statistician would call a parameter space, basically. So you can just think of, whatever it is you don't know. So like a treatment response, the parameter space is, well, the particular thing you're really interested in is the average treatment effect. Is the average treatment effect positive or negative? And so that's the parameter you don't know, and so the state space is all possible values for the average treatment effect, which you don't know before you've collected the data. So first you specify that, as anyone would do doing any empirical analysis. Then you have a very simple thing, is you find if I'm comparing different ways of using the data to make a decision, some are just bad. So no matter what the truth is, no matter what the real parameter value is, this way of using the data to make a decision, let's say I can prove mathematically it's worse than some other way, no matter what the truth is. You would say, well, those are dominated in decision theory language. Wald used the term inadmissible. You throw those out. And then you have the hard part remaining, which is among the things that are what Wald called admissible or undominated, how are you going to choose among them? And this is, I'm an economist. Economists like to talk about optimization. You cannot optimize because you don't have enough information, okay? It's because it could be the treatment B is better than treatment A. It could be the treatment A is better than B. You don't know which way it goes. And so the classic idea of optimization just doesn't work, but you have to make a decision, so you have to think about some way to handle the data. So then this literature on statistical decision theory, the technical literature develops, and it focuses on several criteria. What I have here are the 3 classical criteria, and there are others, but these are the main ones. Maximization of subjective expected welfare. This is basically be a Bayesian, which you can fit into Wald's framework. It says put a subjective distribution on the parameter space of the state space and then do the Bayesian thing. And you can, okay? The other thing, but if you don't want to be a Bayesian, if you don't want to put a subjective distribution on what you don't know, then we have a couple of, we're in a situation that's called decision-making under ambiguity or deep uncertainty. Those are terms that are used in the literature. So if you're going to do it without any probability distribution, the most classic idea is maximin. Look at the worst that could happen to me with any way of using the data, and then do the least bad worst thing. Maximin idea goes back to it goes back to the Bible, really, I think. But in modern times, it goes back, usually viewed as going back to 1925, here at Princeton, actually. It's John von Neumann. Right? Von Neumann was at Princeton, right? And so von Neumann used maximin or minimax the same in 1925. But maximin is viewed as ultra-conservative for good reasons. So then there's another one, which is the one I focus on, and I think is the most valuable, we'll talk more about, what's called minimax regret. And I'll show a bit on the math and then talk conceptually about this, okay? The early literature on applications of statistical decision theory did not apply it to making treatment decisions. The classic problem in the 1940s and 50s was prediction. So you want to get a best predictor under square loss. Everyone knows the best predictor under square loss is the mean of a distribution. But if you have sample data, you don't know the mean, then what are you going to do? And speaking to one, and the minimax regret solution in this case is actually to minimize maximum mean square error. Okay? It's not to maximize R squared. One person here knows what I'm talking about. It's to minimize maximum mean square error. That does solve the minimax regret problem, okay? Now, that work was all done a long time ago. It kind of fell out of favor by the 1960s. And the literature kind of really dries up. Even by the time I was in graduate school, the literature had dried up. And this is before most of you were born. But the fact that you'd probably never heard any of this is not surprising to me at all. I find this routinely when I talk to econometrics audiences as well, that this stuff is just not taught anymore, even though it was very central to the statistics literature in the mid-20th century. Now, what's happened in the past 20 years is there's been a kind of a slow rebirth in which I played a certain role myself, trying to apply these Wald ideas for treatment choice. So I don't just give the sites here, but the full references, if you go on my webpage and get the paper I'm talking you'll get the full cites to these papers. They're all in econometrics journals, basically, is to applying the Wall theory to treatment choice, okay? Now, in that context, Wall's basic notion of a statistical decision function, which is a mapping from the data to a decision, we just call that a statistical treatment rule, just as terminology for that kind of application. And then the mean sampling performance of some decision rule across repeated sampling is expected welfare. Now, if you say this is abstract, what am I talking about? Using a hypothesis test to make a decision is a statistical treatment rule. If I use a hypothesis test, the hypothesis test is giving me a function. So, I take the data, I plug it in, I see what the critical region is, and if the data fall in this region, I choose treatment A. If it falls in the other region, the rejection region, I choose treatment B. So the hypothesis test is a statistical treatment rule. The question is it an interesting one? Does it have good properties? Let me juxtapose that, and it doesn't. Right, okay, so let me juxtapose it with one that's been found to have much better properties, which gets away from all the asymmetry in classical testing, which is to take the sample data and treat it as if it's the population. If you had sample data from a trial, let's say I had 100 observations on people assigned to treatment A and 100 assigned to treatment B, and I look at the survival rate, the sample survival rate in treatment A and treatment B, be a very simple, welfare function. And then if treatment B yields a higher survival rate in the sample than treatment A does, then I say treatment B is better and treatment A is other. So I'm going to call that the empirical success rule. It's just plugging in the sample averages. That's totally symmetric. It treats the error probability is very different, and that turns out to have much better properties from this decision theoretic perspective. So if you're thinking this is all abstract, just think about hypothesis. All hypothesis tests are a certain type of statistical decision function. Just plugging in the sample outcomes and using them to make a decision is a different way to use the sample data. And then, of course, there are millions of other things you could do, but we don't have to get into all of that. Okay. Now, I said we've mainly used minimax regret criterion. Why? Let me see, did I skip something? No, that's fine. So we'll have to get into this a little bit more and see why. Now let me talk a bit about doing this with existing trial data, and then I want to talk about choosing sample size for a trial. And I just hope I'll have some time to say a bit about that. So just imagine the simplest case now. You've got two treatments and observationally identical patients. So what I mean is the patients, of course, could have different covariates, observable covariates, different races and genders and a genetic background, whatever you observe. Let's just condition on them and suppress that, okay? So you get people who look the same, but they all may be people who fall into a certain group. And you have a health planner, and you can assign either treatment A or B to each member of patient population. A little bit of notation, anyone who studies analysis of treatment response will be familiar with this. Each patient has a response function, a yj dot, that maps treatments into outcomes. There's a distribution of treatment response in the population. This is just like standard treatment response notation. People may respond heterogeneously to treatment. I'm not saying everyone responds in the same way, but it's unobserved heterogeneity. We have different genetic makeup. We don't observe it, so people respond in different ways. Okay, now what are we trying to do? We're going to have to specify a welfare function, something we'll want to maximize. And if I think about this, so this is now an OPR problem. This is population health planning, and I'm a health planner, and maybe I want to maximize overall survival rate of the population, or maximize mean lifespan in the population, or something like that. So that's what this says, is that what I can do in my decision, well, I could assign everyone to treatment A, I could assign everyone to treatment B, but I don't actually have to do that. I could assign some fraction of people to treatment A and some fraction to treatment B. So instead of letting delta just be 0 or 1, I'm allowing delta to be anything in between 0 and 1. Okay? Because that could be feasible if I'm a dictatorial health planner. Okay? So what's going to happen in terms of social welfare is that my social welfare, that's my capital U of this allocation delta, this is if I knew the truth. I haven't got to the sample data yet. Well, 1 minus delta of the population, that fraction will go to treatment A, and their mean outcome will be the expected value of YA, okay? And then a fraction delta will go to treatment B, and they're going to get the mean value of YB. Then I just call alpha and beta as shorthand for these expected values, the mean outcomes, and then I can rewrite it this way, alpha plus beta minus alpha delta. Now, obviously, the solution to this is that if beta is bigger than alpha, I should put everyone in treatment B and otherwise treatment A. That should be familiar because beta minus alpha is the average treatment effect. And this explains from a decision perspective why the population-wide average treatment effect matters. And it's particularly, for those of you who take some econometrics and hear about all kinds of other average treatment effects, like local average treatment effects and things like that, this is not that. This is the population average treatment effect that you care about, not some notion of a local average treatment effect. And if the average treatment effect is positive, treatment B is better, otherwise treatment A. The problem, of course, for decision making is that if I have sample data, I don't know the distribution of treatment response. So I don't know whether the average treatment effect is positive or negative. Okay, so here's now the statistical problem. I'm going to use the data. The data, just make this abstract. There's some sampling process. At this point, it doesn't even have to be a randomized trial. It's just some data from something. But randomized trial will be the important case. And there's some sampling distribution. And this delta of dot is a function that maps the sample data, that maps the sample space into an allocation 0, 1. And then the welfare that will be realized is going to be this, because now this is just like I had before, alpha plus beta minus alpha. Before I just had delta, now I got delta psi, because what I do is going to depend on the data that's realized, okay? This is now a random variable. If I look at it ex ante in a frequentist way, before I actually draw the data, I don't know what data I'm going to draw, so I don't know what decision I'm going to make, but I have to I'm thinking about a decision process that works at that level. This is, these are all the state space here. These are all the parameter space, all the possibilities, because I don't know the true value of alpha and beta, and I may not have full information about my sampling process either. And then this is the thing that you care about, the expected welfare in Wald's terms. And now just very quickly, this is the only abstract math, and then I'll get very specific after that. If you want to use the 3 classical criteria that are in the statistical decision theory literature, Bayes' rule would be this, is you put a subjective distribution on the parameter space and then maximize your subjective expectation, okay? That's Bayes' rule. Maximin is for any given allocation, you look at what's the worst that could happen to me. That's the min. So that's the worst that could happen to me if I choose allocation delta, and then I choose the least bad one, that's the maximized delta in terms of these worst cases. That's maximin. So now it's just a math problem. You just have to solve this thing, which could be easy or it could be very difficult computationally or analytically, depending on the structure. Here's min-max regret. Takes a little bit longer to explain, but I can do it verbally actually easier. But for those who catch it with the math, I haven't said what's regret. Regret is this quantity in the brackets. I look at, if I knew the truth, if I knew the true parameter value, I could optimize and I would get the maximum of alpha and beta. Okay, if I knew the truth. But let's say I don't, but let's say I do something else and I choose some delta which is not 0 or 1, and then I do this. Regret is how much worse I would do than the optimum. That's, the word regret is a psychological term, but it's like how much worse I am off rather than doing the best thing. That's sort of psychologically what regret means, and so that's why that term got to be used. But I think it's actually better to say it's like the loss relative to the optimum. That's what regret is. Now, sorry, I keep doing that. I can't, you'd like to minimize regret, but I don't know the truth, so I can't do that. So I maximize over all possible parameter values, so that's now maximum regret. And then maximum regret's a bad thing, and so I minimize maximum regret. So here's the math problem you solve, okay? I'm sorry, I know it's quick, but did you have this very quick seminar? I teach this, I go through it very carefully with my PhD students, but you can look at it and look at the articles to get into it. Okay, now why particularly focus on maximum regret? There's practical reasons and conceptual reasons. First, if you want to be Bayesian and put a subjective distribution down on anything you don't know, I'll say fine, if, okay? I'll say fine if you have a good reason for the subjective distribution. This is, you mentioned the law of decreasing credibility, which is a kind of a silly thing I made up just to make people aware that, it's not silly at all, I think it's fundamental, but you want to make aware that, drawing strong conclusions doesn't come free. We can have really tight models and draw strong conclusions, but we may not believe anything. So that's what that, the problem with being Bayesian has always been is where does this prior distribution come from? And if you feel comfortable with your prior distribution, I'll say, sure, be a Bayesian. Problem is in practice, it gets very hard to think about what's a credible subjective distribution. There's a huge controversy about this in the medical literature, and I could give you references to some interesting articles that go back and forth about that. So I'm just going to say, look, we don't want to do that, and we want to be agnostic and not have a subjective distribution. So then what are you going to do? You could do max and min or minimax regret. It turns out that max and min with a randomized trial, because it's so ultra-conservative, it tells you basically not to pay any attention to the data at all. Okay? I could show that mathematically easily. It was actually first recognized by Leonard Savage in 1951. I gave a little formal proof in my 2004 article. It just doesn't work. Minimax regret, on the other hand, practically works very well in these contexts, and it actually gives a solution in a wide variety of cases that's very close to this empirical success rule, just using the sample average as if it's the truth. Okay? So that's a practical reason. There's also a conceptual appeal, and I think this is what gets to the heart of how different this is from hypothesis testing, is that what maximum regret is, it quantifies how lack of knowledge of the true parameter or state of nature diminishes the quality of decisions. If you have small maximum regret, then you're uniformly close to optimal across all possibilities. And this is particularly simple in this case with two treatments. If you actually, about the math of this maximum regret, it looked a little abstract before, if I just look at regret, not maximum regret, here is what regret is. If I look at a state of nature where treatment A is better than B, then the regret of any statistical treatment rule is the product of the probability of a type 1 error times the magnitude of the loss that occurs when I make a type 1 error. So this is the difference from hypothesis testing, because the hypothesis testing just to look at the probability of type 1 error. Here we just literally multiply it times the magnitude of the loss. Symmetrically, if treatment B is better, then regret is the probability of a type 2 error times the magnitude of the loss when I make a type 2 error. So this is like totally symmetric. And it incorporates the magnitude and basically answers in a very practical way the criticisms I had of hypothesis testing a little while ago. Okay? So that's the conceptual appeal. This is just push that a little bit further. Now, given that I've got, what, just 10 minutes? Or when do you actually stop to take questions? Who's it, you?
Yeah.
15 more minutes. Oh, 15, okay. Okay, well, I'm just racing along here. Okay, so then, now I want to talk about some most recent work, and both of these with Alex Tetanoff. And the first part of the work is about applying this when you already have the data, and then about using it to choose sample size. And I actually want to spend more time on the latter. What we do in this PNAS paper, this is a fairly technical paper, is that we apply this minimax regret rule in 2 trials, and we do the original contribution is that solving these problems of what is maximum regret and so on requires either some analysis or a lot of numerical work, depending on how you approach it. And what we do is we think about using this empirical success rules, because the empirical success rule, using the sample data as if it's the truth, actually is very close to the minimax regret rule. And there are theorems on this, not by myself, but by York Stoyer, who's at Cornell in economics, and a couple of articles in the Journal of Econometrics. Let me just, because going through everything, let me just get to a kind of bottom line in terms of, take a very simple case right here, and then I'll expand on it. And let's say, well, the maximum regret's a bad thing. That's like how far you are from doing the optimal. So you'd like to get maximum regret down to 0. The only way you're going to get, you can get maximum regret down to 0 by taking larger sample sizes, right? But of course, you have to go to infinity to get rid of it entirely, right? So you are going to do a finite sample size, and let's say in clinical practice, well, how close is close enough to the optimum? You could think about this kind of heuristically. You can think about it in Herb Simon's satisficing, as how close to being optimal would be enough. And so you choose a value of epsilon, which is, if I get within 5% of the optimum, no matter what the truth is, I'll be okay with that. Or if I get within 15%. The medical literature has calculations of this type about what's called a minimal clinically important difference between treatment A and treatment B. So we have some discussion about that. The point is, if you choose, the tighter you make your epsilon here, the bigger the sample size you're going to need, because you're going to have a tighter criteria. If you use the empirical success rule here, to make your decisions, this is just numerical calculations, you would need 145 people per treatment arm, treatment A and B. If you were to use hypothesis testing with a standard 5% z-test, this is for comparing Bernoulli outcomes, survival, yes, no, and you're comparing across treatment A and B. This would be a standard test you'd use in the medical literature. It would actually really require more than an order of magnitude more, 3,488 is the sample size. So you need a much, much larger sample size, okay? Let me just go on. In the few minutes I have left, let me make this much more practical. First let me say, why is this important? It's important for some fairly obvious reasons. Is that a huge problem, particularly in medical clinical trials, is getting enough patients to do the trial. And the way the convention, which comes out of hypothesis testing, is by power calculations. You're going to set 0.05 as the probability of type 1 error, and then you have to have a sample size that's big enough to get the probability of a type 2 error down to 0.20, something like that. And the FDA requires that. NIH requires it in setting up trials. You're not going to get your grant funded if you don't have sample size that satisfies these power calculations. So this really matters. Now, if you could, and of course, when you don't have that sample size, you're basically rejected. You say that your trial is so-called underpowered and it's useless, and you can't learn anything, about it. And just give you many quotes from the medical literature about the harms of underpowered trials. So if you view this from a different perspective, from the decision theory perspective, and if you find that you could actually get a sample size that's much lower, maybe 10 times as small, although the case I'll give won't be quite as bad, the specific case I'll give in a moment will be about a quarter of the size, and that's going to suffice for a clinically useful trial, then of course that's important, because it's going to reduce the cost of executing trials. It's going to reduce the amount of time it takes to get subjects. If you know the medical trials, they're very often multi-center trials because you don't have many patients at one place, and they go around the world, combining data from many different centers, and that's all. And this takes a long time. It's very expensive. So if you can do that more cheap with smaller sample size, that's great. The other thing you can do is if you do have the ability or the funds to do the full-scale trial, you could do more treatment arms. Instead of just comparing treatment A and B, you could compare A, B, C, D. Because all the theory I'm talking about generalizes immediately to any number of treatments, which also was a problem with hypothesis testing, okay? So that's the kind of general thing. Now, to push this beyond generalities and the math, Alex and I, this is also coming out in the special issue. I'm going to take the remaining time to talk about this, is to look at reanalyze a particular recent trial comparing surveillance and aggressive treatment. So as I mentioned before, this is a very, very common kind of problem, is that you can do surveillance and it's kind of a light thing, and if the patient's not sick, that's great because they just have a periodic scan and it's non-invasive, but if the patient's sick, you're in real trouble. If aggressive treatment, you'll maybe better chance of curing what's really going on, but there can be side effects, which sometimes could be very invasive or costly financially. So, so there's a lot of trials comparing surveillance and aggressive treatment. They're harder trials to analyze than what's done in the medical literature. And this is why we have to do new analysis in this paper beyond the 2016, is because from a welfare perspective, you should take into account the primary outcome and the side effects together. and you should weight them. It's like, at least what an economist would do, is he would say, I care about whether the patient lives or dies, but I also care about quality of life, and I should put some weight on quality of life and sum the two together. The medical literature does not do that. The medical literature has this very odd thing of being lexicographic. All of the statistical analysis is done by what they call the primary endpoint. It's like whether a patient lives or dies, and they view the side effects, as they call it, a secondary outcome, and it's just some discussion off to the side. And they don't do the trade-offs that at least an economist would want to do between these things. So we had to expand our earlier PNAS analysis to do this. So that's what's new in this paper. The particular example that we use is one that's not particularly well known, but it's an interesting one. It's called lymph node dissection. And this shows up, I'm going to particularly do it for a case of melanoma, localized melanoma. It also shows up with breast cancer. That if you know anything about these diseases, if you had melanoma or breast cancer, they're going to do surgery and try to get rid of the tumor at the spot. But of course, what they're really worried about is metastasis, and they think that the way it gets inside the body, that's what's really going to kill someone, is if it gets inside, is going to go through the lymphatic system. And so what they do is they trace with radioactive dyes which set of lymph nodes the thing is going to, and then they do biopsies of the lymph nodes and see whether there's been any movement of the disease into the lymph nodes. Lymph node dissection is if they find any problem in the lymph nodes, then they just surgically remove all the lymph nodes in that area. This has gone on for 100 years, both with breast cancer and with melanoma. The side effect, obviously the aggressive treatment is removing all the lymph nodes. The side effect is what's called lymphedema, which is kind of a swollen of the arms or the groin or whatever the lymph nodes are. And it's not going to kill you, but it can be debilitating, okay? And the argument that's gone on for 100 years in the medical literature is, should we surgically remove all the lymph nodes, or should we watch the lymph nodes, which used to be by hand, you know. Clinicians are supposed to have good hands and feel things and for tumors, but now it's by ultrasound scans and so on. So that's what underlies this. The particular article is that we're talking about here. This was the lead article in the New England Journal of Medicine in June, in an issue in June 2017. This thing called the multi-center selective lymphodectomy trial, MSLT2, and it got a lot of details. I don't have the time to go through them. For what we have here, the basic point is that using a conventional statistical power calculation, they assigned 970 patients to each treatment arm, 971 and 968. One to the aggressive treatment, removing all the lymph nodes, and the other to the surveillance, which is just the ultrasound. And that's what they thought, to have a sufficiently powered trial, they would need to do that. Alex and I looked at their article. We set up a welfare function where, for reasons that we got out of the medical literature, we decided to say that getting lymphodectomy reduces quality of life. Let's say you get a 1 if you're alive and have no problems at all. You get a 0 if you're dead. If you're alive but with the swollen areas of lymph node, you get a 0.8 instead of a 1. So it reduces it by 0.2. Where do we got that? We actually got that from the medical literature. Is we found an article that actually surveyed patients about how they thought it would reduce quality of life to have this. So this came from somewhere. We didn't just make it up. We chose a value of epsilon, which comes from the way they did the trial. After I finish, if anyone wants the details, I'll explain it more. I just want to get to the bottom line, is after doing this, this is what would be optimal. Treatment A is surveillance, and treatment A, you just either live or die. There's no chance of the side effects, and the treatment B is the aggressive treatment. You're either going to live or die, but if you have the side effect, you subtract something off. The things you want to learn are these probabilities. That's why you're running the trial. And when we did forget about that, just go to the bottom line. And what we came out with, and we're actually, it's one of the rare times in my career where I feel like I'll stick my neck out and actually put out a number, because I'm usually telling people why their numbers are wrong. And so we're actually, but we have to take this seriously, is that we thought they could have done that trial with 488 subjects rather than the 1939 that they actually used. And I think if I were to talk to a surgeon, I'd hope to try to, which I've not done yet, but try to persuade them that that would be a sensible thing to do. Okay, so that's, so let me just conclude, and then we can take the rest of the time to flesh it out. Let me conclude first with a very broad statement about statistical decision theory. I write here that, we'd like to think of the Enlightenment model. Science progresses, we know more and more over time. That's not the way it always is. It is all the time. There are, I think various of you in the room could think of cases where there was something quite important happen, whether it's in a statistical analysis or in sociology or economics or in biology, whatever it might be, where there was some really good idea, there was some work on it, it was in the literature, it wasn't that it was just some totally obscure thing. People paid attention to it, and then it fell out of favor for some reason, and then it just gets forgotten. And then you have to relearn the whole thing. And that's, I really feel strongly, is what happened with statistical decision theory. Abraham Wald was one of the best known statisticians and mathematicians of the 20th century. He was, I get it, since he was not at Princeton, he was at Columbia. He was a refugee from Eastern Europe, but he spent his adult life in Columbia. But there was also a Princeton connection that Oscar Morgenstern, who was here, brought him over, got him out of Austria, and brought him to the US. And Morgenstern was here at Princeton most of his career. So everybody knew Abraham Wald's work. And you may know of a Wald test and hypothesis testing and things like that. But clearly Wald's most important contribution was statistical decision theory. Any statistician in the mid-20th century would have said so. But it just fell out. It just fell out so that even by the time I was in school, the late in the early 60s, early 70s, it was not taught. And I've talked with people who teach, people above age 55 or so may say, oh yeah, I remember statistical decision theory, I've heard about it from this or that, but they don't teach it anymore in PhD programs or anywhere. I now teach it at Northwestern for a couple of weeks, but that's very rare. Around here, there is someone who teaches it, is that Chris Sims teaches it in econometrics. Chris, he's a little dogmatic Bayesian, but he knows this stuff inside out, and I'm sure Chris does a fair job on it. But that's actually quite rare to do that. So somehow it fell out. But there is now a small group that's been trying to revive it, particularly in the context of treatment choice, which is very, very important. I think the treatment choice applications are more important than the original, prediction. I'm not saying the prediction is a bad application, but there's so much work on using randomized trials to make treatment decisions that this is really a good type of application. And so I just want to end and say that I think it's really well past time for people to learn or relearn statistical decision theory and to use it. And a particular motivation is to get rid of hypothesis testing. So so I'll stop there.